Well, it's a great pleasure to begin this series of lectures on gravitational waves. And so what I'm going to do is give you an introduction to gravitational waves from the theoretical point of view. Later, you'll hear lectures on detection of gravitational waves, astrophysical connections to gravitational waves, and other things, but I'm here to give you a bit of the theory. Here's my formal introduction with lists of positions I hold and blah, blah, blah. But if you really want to be my friend during these lectures, you will not use any titles and call me Cliff. Or, if depending on your accent, you can also call me Cliff. And in France, they always call me Cliff. So that's up to you, but I like to be very informal, especially with the more advanced students. Sometimes it's tough to get freshmen to call you Cliff because they say, oh, Professor Will, but you're all senior students, so I think you can call me Cliff or Cliff. And there's my webpage if you want to see more, email, and so on. Now, first I want to ask a question. I'm supposed to introduce gravitational waves, but I want to ask who in this audience, and don't be embarrassed to hold up your hands, who in this audience has never had a single introductory course or any kind of reading about general relativity? You, okay. I mean, if I say metric, Riemann tensor, does anybody, do you throw up your hands and say, what? Maybe nobody. So you've all had something. Well, I'm going to, of course, give a very fast, fast forward kind of review of general relativity. Those will be maybe the first half hour today. But I really want to focus my attention on an approach to general relativity that's called post-Minkowskian theory, that is really the modern way to do realistic, astrophysically oriented calculations of gravitational waves in general relativity. Many of the introductory textbooks that you've seen will talk about exact solutions. They'll talk about linearized theory, say a few words about gravitational waves. But most of that is impractical when it comes to dealing with how do we detect gravitational waves, what do the waves from in-spiraling black hole binaries look like. Those textbook treatments are useless. But there's a modern way called post-Minkowskian theory that really helps people to deal with these complex astrophysical situations for calculating gravitational waves. And so I'll give a basic formulation, then talk about the gravitational wave from the wave zone point of view, where your detector might lie, but also from the near zone, where you need to know what are the equations of motion of the bodies that are emitting the waves. Now, I am a completely shameless self-promoter. There happens to be a textbook that covers all of this material in great detail. If you can reach high enough, you can click here and you will never see this ad again. But you have to have this ad at least once whenever you, engage with the internet. So there it is. It's also available on Kindle. I don't see how you would read it on a Kindle, but on your iPad you could read it. All the equations are there. You can get it on Kindle as well. It's a big, heavy, thick book, but Kindle or iPad is much lighter. I see nodding. Does anybody have the book? You're so great. Okay. So general relativity. The fundamental postulate or the fundamental basis of Einstein's theory of gravity is called the Einstein equivalence principle. It really has three kinds of pieces. The first is that bodies should fall with the same acceleration. And here by body I mean a laboratory scale body, a body that doesn't have its own internal gravity, but it's held together by typical atomic forces. Bodies fall with the same acceleration in an external field with this, independent of their structure or composition. And this has now been verified to parts in 10 to the 15 by laboratory experiments, space experiments, and so on. If you put yourself into a local freely falling frame, a frame that just falls freely through space-time, in which gravity seems to disappear because you're just floating around, then the laws of physics should be Lorentz invariant. And that's just basically a local statement about what non-gravitational physics should look like. And since Lorentz invariance is so well tested in the standard model of particle physics, that's a very natural assumption. And finally, in the same kind of a freely falling frame, physics should be independent of where and when you are in that frame. So basically the constants of nature, the fine structure constant, the quark coupling constant, and so on, should be independent of time and space. And again, that's in agreement with sort of the standard model of particle physics that we're all familiar with. But it turns out if you make those assumptions, you can make a very compelling argument. It's not a theorem because this is physics, not mathematics, but you can make a very compelling argument that the theory of gravity must be what we call a metric theory of gravity. It's a theory where there's a space-time metric, a tensor object that couples to matter, and it's the only object that couples to matter. And you can discover what physics looks like in the presence of gravity by letting the local Minkowski metric of special relativity be converted to this g mu nu, which is the metric of space-time. And you let commas, partial derivatives of the fields that you see in the standard model, become semicolons, which are the covariant derivatives. I'll say a very little bit about covariant derivatives in a moment. But roughly speaking, the argument based on these principles is that gravity is the same as geometry, that the effects of gravity are really synonymous with the effects of being in a curved space-time, that curvature of space-time being generated by the presence of massive objects. Okay, and this is a very universal statement. When I say metric theory of gravity, that does not imply general relativity necessarily. General relativity is a metric theory, but the literature is full of alternative theories of gravity that obey everything I say. The famous scalar tensor theories that you read about today, Einstein ether theory, there's a whole giant literature, especially these days, of alternative theories of gravity that agree with all of this, but just have different field equations. So, a quick review of sort of basic general relativity. And I like to think about it in two parts. This is based on a statement that John Wheeler used to like to make all the time. First statement is curved space-time tells matter how to move. And the second statement is matter tells space-time how to curve. So the first part, if you're in this curved space-time, one way to understand the motion of a particle is through an action principle. You calculate the total elapsed proper time between two events in space-time, event here at one moment of time, an event there at some other place at another moment. Calculate the total proper time. You can write that in terms of coordinates and the metric. You then vary the path, holding the endpoints fixed, so you consider alternative paths between the two same space-time points, and calculate the total elapsed proper time for all of these paths. And the statement is the path followed by an actual particle in space-time is the one that has the maximum proper time elapsed. So you extremize this action by varying the path. This is just what you do in standard Lagrangian theories, right? You change the path and you maximize the Lagrangian. That gives the Euler-Lagrange equations of motion, which in this case look like this. So there's an acceleration of the particle's path. This is a 4-vector, both space and time. Tau is this proper time measured along the path. These are Christoffel symbols that are calculated by taking certain kinds of derivatives of the metric. Greek indices are space-time indices, and one sums over any kind of repeated indices, nu and nu. You sum over all 4 values. And so the acceleration of every particle depends on the derivatives of the metric and also on the velocity of the particle, the 4 velocity. So this is curved space-time telling matter how to move. Now, along with curved space-time, you have a mathematics that tells you how to do things like if you're given a vector field or some kind of a field on space-time, something that has indices and also that can vary in space-time, like the electromagnetic field, how do you calculate its derivative? How do you figure out how it changes from point to point? Well, it turns out in ordinary Cartesian or flat space-time, it's simple. You just calculate the derivative of the components. But because space-time is now curved, these basis vectors also can move around. And actually, this is true even in Cartesian space. Just take the xy plane in Euclidean space. X and y vectors don't change. But suppose you're using curvilinear coordinates, r and theta. Well, the radial vector changes depending on where you go. And the theta vector also changes depending on where you are. So just in simple polar coordinates in flat space, you have to take into account how these basis vectors change. So you can get Christoffel symbols in ordinary flat space if you're using curvilinear coordinates. This just reflects then the nature of the space. So the gradient of a vector then has a part that tells you how the components vary as you move around, but also a part that tells you how the basis vectors vary as you move around. And by the way, the basis vectors are defined in such a way that their dot product are what define the components of the metric. Now, there's a very special kind of vector that we use when we talk about particles moving around, and that's the forward velocity of the vector. So it's basically this thing, the rate of change of the location of the particle with respect to proper time, so that's u. And a geodesic, something that satisfies this equation, happens to be a path that parallel transports its own tangent vector. So the great derivative of this forward velocity along the forward velocity, the component along the forward velocity, must vanish. An example of this is on the surface of the Earth. What is a geodesic on the surface of the Earth? This is flat space. It's just a two-dimensional surface of a sphere. What's a geodesic? Give me an example of a geodesic. The equator, for example. It's a path so that if you move around, you don't veer to the left or the right. Forget the third dimension, you're only in 2 dimensions. All you can do is go forward, left, or right. You don't change, veer to the left or right, just keep going straight. That's what this says. Don't change, go parallel to yourself, but don't change at all. Now, from a 3-dimensional point of view, you're going around the Earth. But if you do this and don't go to the left or the right, you will describe a great circle on the Earth. It's the intersection of the Earth with a plane that passes through the center. That's the equator, any line of longitude, and so on. And with any arbitrary thing, as long as it's that cut of the surface with a plane that goes through the center. So if you're at 45, the latitude of Vienna, and you start heading east, you will not, and you start heading east, the great circle will not be that same line of longitude, because you'll be going around the pole and you'll always be going a little bit to the left, because you're at the top of the sphere and you're going around like this. So you're not on a geodesic. So a geodesic from Vienna will take you along a plane that cuts through the center. Well, that's just ordinary flat space in a particular situation, but this is a general statement. This describes what a particle does if it's moving under no forces whatsoever, known non-gravitational forces. Now, that's particles are one thing, but what we really want to talk about is collection of particles that form a fluid, because we'd like to deal, for example, with how neutron stars behave, how do planets behave, how do stars behave. So we'd like to also be able to describe matter that's described by a fluid, and there's the description in general relativity or in curved space-time. You have a stress-energy tensor, also called sometimes the energy momentum tensor. There's a rest mass density. It's the density of matter, the total mass per unit volume, measured in a local co-moving frame. There's internal energy. It could be magnetic energy, electrostatic energy, all kinds of forms of energy. There's pressure, and it's multiplied by a product of the forward velocity. And then there's another term, which is just the pressure times the metric itself. You can also define a mass current vector, which is the density times the forward velocity that tells you the flux of mass as it moves around. And again, you can show quite generally, this is not general relativity, this is true in any theory of gravity, just the properties of curved space-time, that this thing has a vanishing covariant divergence. So this is a derivative of this tensor. You contract on beta, and this is a covariant derivative, which is going to contain a lot of Christoffel symbols that reflect the curvature of space-time. I'm not going to write down the full formula. You just have to look that up in books. And this current satisfies a kind of equation of continuity. The divergence of this current vanishes. And you may have seen kind of analogs of these equations in non-gravitational situations. The important, this piece is really 4 equations, because there are 4 values of the index alpha, time and 3 space. Turns out that if you take the component of this thing along the forward velocity of the fluid, then you get a very simple equation that says that the rate of change of the internal energy is equal to energy plus pressure times the divergence of the forward velocity. If you play around with that a little bit, you find that that says that for a particular volume of element of fluid that you're following, the change in energy times that volume plus the pressure acting on that volume, on the surfaces, times the change in volume is zero. And what is that called, in other words? A famous law. What's that law? You are allowed to answer questions. Isn't that the first law of thermodynamics? dE plus PdV. Change in energy is the work done. That's the law of, first law of thermodynamics in a relativistic form, valid in curved space-time. It's a very simple result, but it has to be true. It's local physics, right? And gravity doesn't affect things if you're in free fall, so it should be true locally. Then, if you take the other components and study them carefully, you get what's called the relativistic Euler equation. There's a mass density. Notice it's strange. It also includes the pressure times the acceleration. This is the covariant derivative of the forward velocity, is equal to the gradient of the pressure. And this, of course, is just the analog of Newton's law of motion for a fluid. Rho dV dt plus the gradient of the gravitational potential is minus the gradient of the pressure. Here, you see the rho dV dt. Where does the grad u come from? It comes from the Christoffel symbols that are built into this derivative that talk about how the metric varies. So that's where the gravity part comes. And this, of course, reduces to the gradient of the pressure. Okay, so this, in rough terms, in a very fast language, it tells you how curved space-time makes matter move. But now how does matter tell space-time how to curve? Again, I'm hoping that enough of you have had an elementary course in GR that I can say some of these things and just pass over this fairly quickly. From the metric, you construct these Christoffel symbols. From the Christoffel symbols, you construct a particular tensor called the Riemann tensor. It's a four-dimensional tensor, so it has a whole lot of components. So it's given by this string of derivatives. Notice there's a linear derivative plus something quadratic in the Christoffel symbols. From this tensor, you can form something called the Ricci tensor by contracting, summing over all the values of mu. Take this top one and that one, make them equal, and then sum. You get a two-dimensional tensor. Then from that, you can use the metric to contract on these indices. You sum over all the indices, you get a scalar called the Ricci scalar. So this is invariant under coordinate transformations. Then you combine some of these pieces together to form the Einstein tensor. It consists of the Ricci tensor, the Ricci scalar, and the metric. So it's a particular tensor. It happens to satisfy an identity, very important identity, called the Bianchi identity. The divergence of this with respect to beta vanishes. And this is an identity. It's true in any space-time. You have a metric, calculate all these things, calculate this divergence, you will always get zero. So it really is an identity. It doesn't constrain anything. It's just a particular property of these tensorial quantities. Einstein's equations then take all this and the stuff I've talked about before and make a specific proposal that space-time curves according to this equation. You insist that the Einstein tensor should be proportional to the energy momentum tensor of matter with certain constants in front. So those are Einstein's equations. Other theories of gravity get some of their equations in a completely different way. Some of them add other fields. Some of them have completely different constructions. This is general relativity. You can also derive these Einstein equations from an action that consists of integrating the Ricci tensor with a square root of minus g to make it a density type object, integrate over all space-time. Then you have a similar action for the matter. Then, again, using the calculus of variations on this object, you get this equation, Einstein's equations. So Einstein simply postulated this, but it was actually Hilbert, around the same time, they were actually in competition as to see who would get there first. Hilbert proposed an action principle for Einstein's equations, and we now know that they're both the same thing. Excuse me. Okay, so who's out of breath? And this is, I'm sorry, one has to speed along because I really want to talk about the modern way of doing gravitational waves that's certainly based on all of this, but it's a rather different approach that I think many people don't really know. So now I turn to this different approach called post-Newtonian and post-Minkowskian theory. So first, I'll describe the formulation, which actually dates back to the 1940s, even a bit earlier. People started thinking about different ways to formulate those equations of Einstein. And this particular way that has now become the foundation for post-Minkowskian theory was worked out by Landau and Lifshitz sometime in the late 40s, but it first appeared in one of their famous textbooks on physics that they wrote in the late 40s, early 50s, that have now become sort of, historical Bibles of many fields of physics. But I think that's the first place where they actually wrote them down. I don't think they ever published them in any papers. They worked it out and then put it in their textbook. So we now call it the Landau-Lifshitz formulation of general relativity. So here's how it works. We've talked about the metric, G alpha beta. Take the inverse of the metrics. That's why the indices are upstairs instead of downstairs. That denotes that you're taking the inverse of the metric, multiply it by the square root of the determinant of the metric. And the minus is there just because, as you know, in the limit of a flat space-time, the metric is minus plus plus plus. So the determinant of that tensor is always negative. So to be able to get a square root, you have to stick a minus sign in. That's just a convention. That forms another object called we often call it the Gothic metric density, because a typical notation is to use a Gothic version of the G. So form that object. From that object, form this quantity, H alpha mu beta nu. So it's a product of two of these things minus a product, but it's constructed in such a way that it's anti-symmetric under interchange of the first two indices, and anti-symmetric under interchange of the second two indices, and symmetric under interchange of the pairs. And you can stare at it long enough, you can see that that's true. It's actually the same symmetries as the Riemann tensor, which is anti-symmetric under the first two and the last two, and symmetric under the pairs. Form that object. Okay, so you say, so what? Big deal. Well, it turns out that if you take two partial derivatives of this, now we're leaving the world of covariant derivatives. We're not talking about things that are generally covariant anymore. We're picking a coordinate system. Now, some of you may say, what? How can you do that? General relativity is supposed to be generally covariant, invariant under any coordinate system. The problem is, of course, if you want to do a real calculation, a real live calculation in the real world, you have to pick a coordinate system. You cannot do anything in a generally covariant way that is realistic. You want to figure out what the orbit of Mercury is around the sun and calculate the relativistic perturbations, you have to pick a coordinate system for the solar system and do it. You cannot do the calculation in a completely covariant way. It's just practically impossible. So this is not such a big step, but it's a very practical step. Getting rid of, you probably won't see a covariant derivative for the rest of the lecture. It's all going to be partial derivatives. Things will depend on coordinates. The only thing you have to remember is that at the end of the day, when you think you have a prediction for something, you have to express that prediction in some kind of coordinate invariant way, using invariant things like scalars and other things, because physical answers that you measure with a piece of equipment cannot depend on coordinates. The output of LIGO doesn't depend on the coordinate system we use to describe LIGO. But that's at the end of the day. The path you get there can use whatever coordinate systems you want to use, and as long as they're convenient and useful. So, but this H alpha mu beta nu has a fantastic property that if you take two partial derivatives, contracting on nu and contracting on mu of this object, you get something that is exactly the Einstein tensor plus something else. Well, the Einstein tensor is proportional to the stress energy tensor of matter. The something else turns out to be what we now call the Landau-Lifshitz pseudotensor. This has a remarkable property. This object is quadratic in first derivatives of the Gothic metric. And that'll prove to be important as we move along in the lecture. Okay, so it's just this thing has this beautiful property that if you take two derivatives, you get something that's just the standard energy momentum tensor. There's a minus g, not square root, but the full, plus this object that has a very particular structure. So these are called the Landau-Lifshitz version of general relativity. And this is not an approximation. These are still exact. This is equivalent to the exact Einstein equations. Okay? Except that we've chosen a coordinate system and it's expressed in a coordinate-dependent form, but it's exact. Now, very important property of this thing is that if I take another derivative here, suppose I take a partial derivative with respect to beta of this thing, what can you tell me about the answer? What should the answer be? And you don't have to calculate anything, you just have to stare at it. So there's a partial with respect to beta, and I'm going to sum on beta. What should you get? I have a partial of beta and a partial with respect to mu. What do you know about partial derivatives? They commute, right? So if I reverse their order, I don't change anything. But what if I reverse the order on the h of mu and beta? What do I get? I get the minus, I get the negative, right? So that means that that partial derivative with respect to beta is the negative of itself. And what is the negative of itself? 0. So the fantastic asymmetry tells you if you take another derivative and contract, you get 0. That means that's the same thing as the derivative of the right-hand side. So this is kind of like the derivative of the energy momentum tensor that we saw before. In fact, there it was. The covariant derivative of T alpha beta vanishes. That was our equation of motion. That was how matter, responds to the curved space-time. This looks almost the same, except it's a partial derivative. And there's an extra piece, the Landau-Lifshitz pseudotensor. But it turns out that you can prove that these are formally equivalent to each other. A few technical details that I won't go into, but they're the same thing. This acts as an equation of motion for matter. But because of the partial derivatives, you have to have something else to represent all the gravity that's embodied in the Christoffel symbols in this version. But the two versions give you the same thing. Now, we'll see in a moment why that's extremely useful for thinking about it, especially when you start thinking about gravitational waves. Are there any questions so far? And you have to shout, I'm old and I have hearing aids, so, or come to the front, or, hold on. Well, in 1947, of course, they were barely thinking about gravitational waves. I mean, people thought they should exist, but no one ever thought about detection. But there was a thread, especially in the 1940s, of people just trying to find formulations of general relativity, and there was a big worry about that time about what does conservation of energy mean? Because energy can't be defined locally in general relativity. If a body with some energy, you can change your coordinates and then, it can be anything you want. So they were worried about what is the proper definition of energy. So that was one motivation for looking at these things. And we'll see at the next slide why this formulation actually gives you a nice answer to the question of what is energy, total energy of a system. Okay, so here's your answer. So for example, T00 for matter looks like energy. It's sort of like the density, right? So let's define an energy of our system, total energy of the system, just to be the right-hand side of the Landau-Lifshitz equations, but using 0, 0 for the components, the time-time components. That's like an energy density. So if we calculate this thing integrate over all space, let's call that the energy. What is the rate of change of that object? So calculate d by dt. So it's d by dt of this stuff in here. But from the previous equation, d by dt of this is equal to minus spatial gradient, right? Because when you sum over all four, you get 0. So d by dt is the same as minus grad J and grad J. So the answer is that this d by dt of this becomes, I may have lost a minus sign, but there's 0j. So there's a divergence with respect to j of this. If you have a divergence integrated over all space, you can convert that into a surface integral, right? And that's the beauty of partial derivatives. You can do that with partial derivatives. You can't do it with covariant derivatives because you have all these gamma Christoffel symbols hanging around. You don't know what to do with them. With a partial derivative, d by dt of this is equal to the ordinary divergence of t0j, so you can convert this into a surface integral, and you get this. And this looks like a flux of energy. Now, where did t0j go? Well, here we're just assuming that our matter, our stars, our bodies, are not emitting some wind of particles or not emitting an enormous flux of neutrinos that might affect it. We're assuming that their matter is localized to where they are and not blasting out to infinity. If they are, you have to take that into account. But here we'll assume our bodies are localized, so at a surface at great distance surrounding the system, the only thing that there is this object, which remember was constructed from the gravitational fields. Those Gothic G's. So this looks like a flux. And indeed, we'll see that it is the flux of gravitational waves. So the system's energy changes if it's radiating gravitational waves. This is where the kind of thing that they were looking for, and I think it was Landau Lifshitz who gave, in the end, the proper formulation that gave them very nice properties. In fact, within this formulation, you can do the same thing. You can define a momentum of the system. So it's the J component of that object. And that is conserved unless there's momentum being radiated to infinity. You can define an angular momentum, and it kind of looks like what you'd expect, right? It's the cross product. This is the so-called Levi-Civita symbol. It's completely anti-symmetric under interchange of the pairs, but it's like taking the x cross p, right? X cross p is j, the angular momentum. And again, the rate of change of angular momentum, you've got an expression that looks like the angular momentum flux at infinity. And you can also define a center of mass of the system in a suitable way. So these are very nice properties. Now you might be puzzled by this thing about radiating momentum. How can you radiate momentum? It turns out astrophysically this has turned out to be a very important aspect of gravitational waves. If you emit gravitational waves in an asymmetric manner, suppose you emit more in this direction than in that direction, that means you're emitting more energy in that direction. That means more mass in that direction. And it has speed c, that means more momentum in that direction. So your system has to recoil in response because total momentum must be conserved. And indeed, we have found, especially through work in numerical relativity, that if you have asymmetric binary black holes merging, one black hole more massive than the other, and if they also have spin, which enhances the effect, the final black hole that's produced after they've radiated gravitational waves can experience a kick, can have a net momentum, and in some simulations they're as high as thousands of kilometers per second, enough to eject them from the galaxy in which those black holes exist. And there's marginal observational evidence of some of these black hole kicks, and they're certainly a very important aspect of gravitational wave astrophysics at the moment. But this Landau Lifshitz formalism gives you a very good way, precise way to calculate what the kick is from a given situation. Okay. I started out with choosing a coordinate system, and the coordinate system is just basic x, y, z, t coordinates. But now I'm going to specify them a little more precisely. And I'm also going to assume that our gravitational fields are rather weak. Now, this is a good assumption unless you get too close to a black hole or too close to a neutron star. But if you really care about the orbits of two objects relative to each other at velocities that are smaller than the speed of light, then the field of one body seen by the other is weak. And of course, as the gravitational waves propagate toward your detector, they're getting weaker and weaker and weaker as they spread out. So a weak field approximation seems like a reasonable one to make. And so within that approximation, we assume that our Gothic metric is a small deviation from the background flat space-time metric that we've constructed. And remember, we're staying in Cartesian coordinates throughout this. So we define these potentials, and these will be called the gravitational fields, and we're going to, this assumption implies that they're going to be small in some suitable sense. I'm not going to make that sense precise, but small. Then we impose one more constraint on our coordinates. We require that this H alpha beta have vanishing divergence. Remember, this is a partial derivative. Take the derivative, contract on beta, you should get 0. Now, this should be familiar to some of you if you've studied electrodynamics. You have the Maxwell tensor. You define a vector potential whose antisymmetric derivative is equal to, gives you the E's and the B's, right? And then when you want to actually do some calculations, you impose Lorentz gauge on that vector potential. The divergence of the vector potential is 0, right? You do that in E&M all the time, and then you can calculate all kinds of things in electromagnetic theory. So this is the tensorial version of that Lorentz gauge. You just take the divergence on one of the indices. This is a tensor, not a vector. Take that divergence, make it 0, and that's sometimes called Lorentz gauge. And by the way, it's Lorentz gauge. It's not Lorentz gauge. This is Lorentz, who is not a different physicist from the early part of the 20th century from H.A. Lorentz of Lorentz transformations. So there's Lorentz transformations and there's Lorentz gauge, two different people, just letting you know. My collaborator, Eric Fazon, was a real stickler about this point. He says, so many people don't know it, so we must make it clear that it's Lorentz. By the way, the coordinates that satisfy this thing are very interesting from a mathematical point of view, because you can show that if this is true, and this will be an exercise for tomorrow, then if you take each coordinate, x, y, z, and t, and assume that it's a scalar field in space, then it satisfies an equation in which the curved space-time D'Alembert of that scalar field vanishes. Now, mathematicians love these kinds of functions. They're called harmonic functions in any space, of any dimension, any kind of space. It's a function that satisfies this curved wave equation called a harmonic function. And they have very special properties, and mathematicians love them, but this is why we often call this also harmonic gauge. And in the exercise tomorrow, we can work this out. The thing is, when you do this and impose this extra gauge, then these Landau-Lifshitz equations take on a very, very beautiful form. You end up with a wave equation for this field H, where this D'Alembertian is the flat space-time D'Alembertian, not the curved space. And it's just, minus d by dt squared plus the Laplacian of the field. Very simple. The right-hand side is our old friend, the matter energy momentum tensor, plus the Landau-Lifshitz pseudotensor, plus another little tensor we call the harmonic pseudotensor, which comes from the nonlinear bits that used to be on the left-hand side, and we just push them over onto the right-hand side. But the left-hand side is a beautiful thing because flat space-time wave equation, we know how to solve that, at least formally. Right? We know the Green's function for the D'Alembertian. It's a very simple thing, and we'll see it in a minute. So this allows one to really attack these problems in some detail because we've put it into such a very simple form as a differential equation. This harmonic bit is also quadratic in these small fields. Landau-Lifshitz is quadratic in these small fields. So you see the nice property? We have something that has the matter plus things that are small and they're quadratic. On the left-hand side, we have a thing that's linear. So if H is small, this side's going to be smaller still. So we could imagine doing perturbation theory and iterating, get a solution, plug it back in, find a solution, plug it back in, getting more and more accurate as we go, because these are just small corrections. And we'll, again, see that in a moment. And this thing still satisfies the property. This right-hand side has the same kind of conservation law that this divergence vanishes, so we can still define the energy and momentum, angular momentum of the system. And this is still exactly equivalent to Einstein's equations. I have yet to make any approximation. I've said we're thinking about H as small, but I haven't thrown away anything yet. I've kept everything. Okay? All right. Okay. So I'm just repeating this kind of structure, but here are our equations. Matter tells space-time how to curve. Here's your matter plus fields themselves. That tells you what the fields are. Once you have the fields, then those fields tell matter how to move. There's Wheeler's vision fulfilled in some sense. But you might say, wait a minute, we want to find H. But H is over here on the right-hand side. How do we do that? The problem is the same as you have even in exact general relativity. The metric is everywhere, and you have to find solutions for the metric that are consistent with Einstein's equations, but also consistent with the equations of motion. So it's a self-consistent problem no matter what you do. This is true in almost any nonlinear theory. But because H is small, in the next slide we'll see a way for solving for H by iteration. So the idea is that to take this object, this is our field equation, and solve for H as a functional of the variables of matter. Notice I didn't say a function, a functional. In other words, it's an expression, an abstract expression that's a function of the variables of the matter. We don't know what those variables are doing yet. We don't know how they're varying in time. We don't know what the densities and velocities of the particles are yet, but we can leave them as abstract quantities and write down something that is a functional of those quantities. What are those? How do we get those quantities? How do they vary in time? Well, we use these equations, the evolution equations, that will give us those functions of time. And if you do this self-consistently, then you get an expression for the metric as a function of time and all the variables as a function of time. But you have to do it by iteration. And here's where our smallness assumption enters in, and here's where we'll start to approximate. You take, suppose you've gone, iterated n times, so you have H up to the level of n iterations. You take this equation, solve for the n plus 1th H. Take that and plug it back in and solve for H n plus 2, and so on. Just keep solving. Meanwhile, for any level, you use this and solve this equation to get the matter variables as a function of time up to that order of iteration. The starting point, of course, is to put on the right-hand side 0 for H. No metric, no gravity whatsoever. So stick 0 into all the expressions here and solve once. That, of course, from your textbooks is called linearized general relativity, right? No H on the right-hand side, you just solve for the H. It's linear GR. And then take that solution for H1, plug it in, and get H2, etc. And this expansion, you can see, is going to be an expansion in powers of G, because every time you solve, you get a power of G here. If you plug this solution back in, the next one's going to be G squared, and so on. So you get an expansion of powers of G, and this is where the name post-Minkowskian comes from. Maybe terminology invented by our colleagues in Paris. Okay. Any questions? Yeah. I'm sorry?
Could you do this?
I mean, you can, and people have tried it, but it's much more cumbersome than this method, it turns out. In some specific situations, it has been used, but they tend to be very specific and just turn out not to be as general as this. And also, one important part of this is that you get these conservation laws for energy, momentum, these global conservation laws, which is very difficult to get in if you stick with the covariant version of Einstein's equations. Any other questions? Okay, well, I think we've reached 2:20, which is the nominal time to quit. We for coffee break, I think. Is that right? The organizers are not saying anything. Was 2:50? Oh, excellent. You're right. I started at 1:30. You're right. Okay. Perfect. So sorry to get your hopes up. Okay. Now, I mentioned the nice thing about this set of equations is that we know the Green's function for the flat space-time D'Alembert. And I want to talk a little bit about this in a bit of detail because there are aspects of this that are important for gravitational wave calculations. And for the next little bit, I'm going to throw away the indices just to not clutter everything up and just talk about a simple scalar field that satisfies the flat space-time wave equation with a source mu. Okay? So this is just a simplified version of that because I really want to study the structure of solutions of this equation. But we know what the structure is. Psi, you can write it down. You take this mu as a function of spatial variables, you integrate over all space, x prime, but you don't integrate over just holding time fixed because the field that you see for the field x at the field psi at a position x depends on the behavior of the source at an earlier time because the field propagates at a finite speed. So what you feel today depends on the behavior of the source at some earlier time given by the distance between you and that point in the source divided by speed c. Right? It's a retarded integral. And of course, you have to divide by the distance because that's just part of what the signal gets weaker with distance. But the important thing is that it's at a time, the signal at this time t depends on the source at this time t minus this distance. And notice this distance varies with x prime. If your source is a distributed source, it will vary depending on where you're integrating within the source. The point source, fine, it's just one point. But we want to talk about realistic sources like neutron stars. So you integrate over the whole source. Well, you can describe this integral. Many of you are familiar with this from electrodynamics. It's the same thing you get for the vector potential in E and M, except this is the charge density and that's the vector potential. So you've seen this before, I'm sure. But I want to talk about what this looks like in space-time. And what it looks like is this. You have your point x. This is where you want to find what psi looks like. So it's a particular point x at a particular time. So this is a space-time diagram with spatial axes along this way and time plotted upwards. So I want to know the field here at this time. So this integral involves integrating the source over all space, so everywhere, but at a time given by this time minus this distance. So if I'm over here, then time minus that distance is like that. If I'm over here, it's just like that. And so the integral is really an integral over this past, what's called a null cone of the field point x, where we want to get the field. Right? Because for any x prime where you want to do your integral, you have to look at a time earlier given by that distance. So what you're really doing is integrating this source over the past null cone of the field point. Now, if this source consists of some blobs of matter, typically they're confined in some location, like two neutron stars orbiting each other. And so the two blobs of matter are going to be, say, here, going around each other as a function of time. Now, in this field, in this game, we're going to assume that the motions are slow compared to the speed of light. That goes along with the weak field assumption. If gravity is weak, the speeds are not high, and even within spiraling compact binaries, the speeds are still a tenth of the speed of light. So that's reasonably small. It's conventional then, and this is done in electrodynamics, in fact, in any wave-like theory, to divide the region of space into two regions, one called the near zone. So that's all the points in this integral that are within a radius r of the source, where r is of order one wavelength of the waves that are being emitted by the source. Here, one gravitational wavelength. And roughly speaking, a wavelength of gravitational waves is of order of the period of the waves. Again, I'm using if period times c, no, divided by c, no, times c. Period times c is roughly the wavelength of the waves, right? Well, if the bodies in your system are moving with a characteristic velocity of v, and s is the rough size of your system, say distance between your two bodies, then that wavelength is given by roughly s over v. Size over velocity, again, that's like the period. Gives you the time it takes for the two bodies to go around each other once, traveling a distance s with a speed v. So we divide space into a region that's inside that value and a wave zone where r prime is larger than r. Right? This should be familiar from E&M. There's the wave zone where the waves occur and the near zone within one wavelength of the source. Well, that condition describes in space-time what's called a world tube. So it's a thing of fixed radius r, but as time goes on, it just moves upward in time, with the center at the source, the two little bodies orbiting each other as time goes on. So this D, it's called a world tube, is this boundary between the far zone and the near zone. It's a three-dimensional surface, 2 dimensions in space, like a sphere, but another dimension because as time goes on, it moves upward in time. Now, most of the source, the mu, is going to be given by the matter. That's the dominant source of mu. It's the masses and things that are moving around. So most of this mu is going to lie within the near zone. And so the integral of the field at x is going to be dominated by the intersection between this near zone and this null cone, which is this surface surface n. Okay? And again, down in the middle here are our two bodies going back and forth around each other, performing a kind of helix as time goes on. And so we can split this retarded integral up into two pieces. One, an integral over n. So it's an integral of this function over this little tilted patch on the null cone. And then side w, an integral over everything else. Okay? And that would give us the solution of that wave equation. So let's look at the two different pieces. First, I want to look at the near zone. I want to look at this piece. It looks pretty complicated because the surface is tilted in time. You know, this time is earlier than that time. It's got a little shape to it because it's on the surface of this null cone. It looks pretty complicated for doing an explicit integral that we want to do. So the way to get around that is to expand. And again, this is like the multiple expansion you do in E&M. You realize that our field point, which is out here near a detector, that x is much greater than x prime, an x prime that's within this near zone. So we can expand in powers of this small ratio, x prime over x. So in particular, you expand this retarded time bit, assuming this x prime is small, and you can get just a sum over L from 0 to infinity of things that involve multiple derivatives of this function and products of x prime. L just stands for L products, xi, xj, xk, xm, L times. So you can simply easily do this kind of an expansion. And this is a fancy way of describing the multiple expansions that you'll see in, say, Jackson's electrodynamics. And so putting all this together for the near zone part of the integral, that's the integral over this, we're writing it as an infinite sum of these things, but now everything's at a constant time. Tau is this fixed time, t minus the distance from the source, the center of the source, over c. What we've actually done is replaced an integral over this surface, which is varying in time and has a funny shape, with an integral over this surface, which has constant time, which is nice because you don't have to worry, you can fix time and just worry about spatial variables. Well, those two are not the same, but we've done a Taylor expansion to express the data on this surface in terms of the data on that as an infinite sum in a Taylor expansion. So that's all this is. A Taylor series that gets the information from this surface down to this surface of constant retarded time. So r is simply the distance between the field point and the center of mass of our system. The problem, of course, with doing this integral is that the integrals will depend on this radius that we've chosen, because we're only integrating from here to here and here to here, out to the edge, the boundary between these two zones. So the results surely are going to depend on that r. So we have to keep that in mind for the moment. Now, what about the rest of it? I said there's an integral over W. And the point is, in electrodynamics, you never have to worry about that. Why do you never have to worry about the integral over the rest of the null cone in electrodynamics? Because there are no charges out there. Your charges are the source. Say the charges in your antenna out here. As long as there are no charges out here, the source is zero. Why is it zero? Because electrodynamics is a linear theory. The electromagnetic field does not generate electromagnetic field because it's linear. Only charges generate electromagnetic field. So the only integral you ever have to do in E&M is this, which you turn into a multiple expansion into an integral like this, and you get, quadrupole radiation, dipole radiation, all the radiations you get when you calculate antennas and all kinds of stuff in E&M. You never have to do this integral. Okay? But as we've seen in gravity, you have to, because of that Landau-Lifshitz pseudotensor. It's produced by the fields, and the fields exist everywhere in space-time. So you have to now turn to this outer integral because there's source of gravity out there, because gravity itself generates gravity. How do we do that? And here it gets even more complicated, and I'm not going to expect too much understanding. You can, this is not an advertisement. You can read Poisson and Will to get more of the gory details, and plus the original literature where a lot of this was developed some years ago. And what you do to do the outer integral is to recognize the fact that Landau-Lifshitz pseudotensor, which is also going to contribute to gravity, has a particular dependence on space and time that allows you to replace the integral over d3x, which you had before, with an integral over two of the variables, the angular variables, theta and phi, and over another variable u prime that is given by this. Now, it's just an abstract equation, but what it really is telling you is that you're integrating, for a given value of this u prime, you're integrating over the intersection between the null cone that we're looking at. Here's the field point we want. There's the center of our gravitating system. I haven't shown the near zone just to keep it simple. You're integrating over this intersection between the past null cone we're looking at and a future null cone emanating from the source. This is a three-dimensional hypersurface. Varies in time. Notice t is different here than it is there, so it's going to vary in what looks like a complicated way. And then you integrate over angles around the source, so it's 3 dimensions. But that third dimension is a complicated combination of space and time, but it's tailored to the behavior of those fields that contribute. And then you integrate over this variable mu prime from -infinity up to the present. And so you get a series of integrals along these intersections. Here, as this future null cone gets higher, you see that the integral intersects the near zone, so you have to integrate from here around the backside and come back to here. So you cut off the integral at the boundary of the near zone. And the final point is when these two cones are just touching each other, there's a little bit integrated from x back to the tip of that near zone. And this integral, of course, has come from -infinity, so you have these cones coming from -infinity, in each case, doing this intersection. And that gives you this W integral. And the reason you have to do it is that there is source out there, and that source is the gravitational field itself. Now, we'll see later that these contributions tend to be small. They're higher order in what's called a post-Newtonian expansion, but it turns out they're important, and LIGO has detected them. So these are important effects that have to be taken into account. But it really requires that you take seriously the idea that this integral is over a cone, and you have to integrate over the near zone and over the far zone. The amazing thing is, although it shouldn't be amazing, is that when you take this solution, which remember depended on r, the radius of our near zone, this one also depends on r, for example, because you have to cut it off here. But when you add them all together, you discover all the dependence on r cancels. And you can show this in many different ways. And of course, it has to cancel. The r I picked was some arbitrary number. It was, right, 1 gravitational wavelength. I could have picked 3 gravitational wavelengths. The answer can't depend on that thing if I do the full integral, right? And indeed, you can show explicitly that it doesn't. So that actually is a good hint and a tool for helping to do explicit calculations in this area. So, and in fact, this integral gives you, doing this integral, outer integral, gives you one thing that is a very important part of gravitational wave signals. And that's something called the gravitational wave tail. So, again, we're looking at a field point far away near our detector. Here's the near zone. Here's our intersection of N. There's where most of our matter lies in some very tiny world line here. One contribution that you get from this outer integral is called a tail, and the physical reason for this tail is the following. Of course, most of the signal comes from where the source is, right? And that signal travels at the speed of light up the null cone, hits our detector here and now, right? But it came from there then. Right? However, some of the signal could have been emitted earlier in the history of the source. It's emitted earlier, it comes out, and it scatters off the space-time curvature that the source itself is producing. Remember, gravity is nonlinear. Gravity interacts with itself. And so just the static space-time curvature produced by your two bodies in your source, that can interact with the gravitational field propagating and produce a new gravitational field that reaches us. So we can also get a signal today that came from an earlier time in the source, but that signal went out, was scattered, and finally reaches us. You can get one from even earlier that comes out, scatters, and reaches us. So what we see then is a combination of kind of the direct gravitational field plus this delayed gravitational field, which is often called the tail, because of course it sort of comes at the end. It follows the dog. You see the dog's face first, but the tail comes, actually comes at the same time, but it's from an earlier time in the source. And these have been calculated, they've been detected, their effects are seen in LIGO signals, so this is all real stuff, but you need to do this careful integration over the whole null cone to get it correctly. But that's not all. We're not done. That's the wave zone. That gives us the waves that propagate to our detector that depend on the behavior of the source. But how does the source itself behave? We need to know what are the fields within the source. What are the fields between this neutron star and that neutron star that govern how those two neutron stars orbit each other and what their velocities are, et cetera, so we know what waves they emit. So to get that, and since both these objects are well within the near zone, to get the interaction between these two bodies, we need also the fields within the near zone. So here I've drawn the picture. Here's our near zone, far zone boundary, world tube. Our matter is down here in the center. And what we need is, what are the fields here inside the near zone so that we can, say, find the equations of motion for the two bodies. Well, you do the same kind of trick. You look for something small that you can do a Taylor expansion about. Well, in this case, the small quantity is not x prime itself, when x was way out in the far zone. It's this total quantity, because x and x prime are both within the near zone. So this is a small quantity compared to t. So we expand our things in powers of this object. And so it's not a multiple expansion. It's an expansion in powers of c, because each time you do a Taylor series, you get 1 over c. So it's a sum over L from 0 to infinity. There's a c to the nth power, L time derivatives, because you're taking this, doing a Taylor series of this small correction to the time, and then mu at a constant time. In fact, it's the time of this moment times powers of this distance, x minus x prime. So this is what you end up with. And this is actually called a post-Newtonian expansion, because you can see it's an expansion in powers of v over c. Every time you hit d by dt, you get a v, because that's what's velocities that are making your system evolve. So d by dt produces a v, and then we have v over c for each of these things. So it's an expansion in powers of v over c of the field, and that's often called a post-Newtonian expansion. These potentials here are instantaneous. There's no more retardation. Everything's done at time t. So we've taken the data on this intersection, which is actually this little vertex piece of the past null cone. That's a little artifact of PowerPoint. And again, done a Taylor expansion to take this data and just evaluate it using a series on that constant time surface. Okay, so that gives us a nice representation of the near zone fields, and we use those to study the equations of motion for our bodies. But you also have to calculate the far zone bit, all the stuff down here, using the similar techniques as before to get any effects that occur. And indeed, there are tail terms in the equations of motion.